In this video, we're going to check out the momentum method. Well, momentum is a measure of how hard it is to change the velocity of an object. And the equation for momentum of a single object is really simple. It's just mass times velocity, where P stands for momentum. The units are kilogram meters per second. And the really important thing, or one really important thing to know about momentum, is that it's a vector. So there are a lot of steps to the momentum method. The first step is to draw a labeled picture. Second is to determine the positive and negative directions. Third is to draw bar graphs. AP Physics C Mechanics is expected to show motion maps as well. They're supposed to write a momentum conservation statement like momentum is conserved. And if it's true, they're supposed to either write inelastic or elastic and state why either kinetic energy is conserved or objects stick together. Step 6 is to write a general equation like the initial momentum is equal to the final momentum, and then to write in the specific equation, in other words, plugging in the masses and velocities without numbers. So step 7 is without numbers. Step 8 is when they put in, steps 8 and 9 are when you put in the actual numbers. Okay, so this is one of the strategies we're going to use in conjunction with the momentum method. So in a closed system, we say momentum is conserved. So the initial momentum is equal to the final momentum. So the conservation of linear momentum can be split up in, it can be looked at 3 different ways. If the setup is completely elastic, then kinetic energy is conserved. If it's completely inelastic, the objects stick together. And most collisions are somewhere in between. Okay. The strategy we use for collisions is this. If the problem says elastic, we start with this equation, which is essentially this equation for a two-body collision, and P initial is equal to P final. Otherwise, we just use P initial is equal to P final. Okay, so let's stick with a simple problem right now. Let's just look at a problem like this. Let's say a problem asks us, what is the net momentum of this system before and after the collision? So step 1 is to draw a labeled picture, so it's already there, that's done. Step 2, let's call it to the right positive. Step 3 is a bar graph. Okay, so here's our before and after bar graph. We should have a bar for each mass. So the 2 kilogram mass is 2 times 3, or 6 kilogram meters per second. The 1 kilogram mass is 1 times 7, but the 7 is going to the left, so that's going to be negative 7 kilogram meters per second. Okay. And our system includes both objects, but notice afterwards we have no idea what's going on, and that's okay. Step 4 is to say that the momentum is conserved. Step 5 says to include, if true, whether it's inelastic or elastic. Well, it didn't tell us that, so we can skip step 5. We don't know whether the objects stick together, and the problem didn't tell us whether it's an elastic collision or not, so we can skip step 5. Step 6 is to always write out that the initial momentum is equal to the final momentum. Step 7 is to write the specific equation. So include each of these values. Let's call this M1. So M1 times velocity 1 plus M2 times velocity 2 is equal to M1 V1 after. So that apostrophe means after the collision, and then M2 plus V2 after the collision. So these are that's the net momentum after the collision. This is the net momentum before the collision. Then we go ahead and start to plug in our values. Okay, we substitute the correct values. The 1 kilogram mass is going to the left, so that's negative 7 meters per second. 2 kilogram mass is going to the right at 3 meters per second. So 1 times negative 7 gives negative 7 kilogram meters per second. 2 times 3 gives 6 kilogram meters per second. The right-hand side, we still, the problem didn't tell us what's going on with the velocities afterwards, so we're just going to leave them the way they are. Afterwards, the next step is to just add these up. Negative 7 kilogram meters per second, negative 7 kilogram meters per second plus 6 kilogram meters per second equals negative 1 kilogram meters per second. So we know that the net momentum before the collision is negative 1 kilogram meters per second. That must mean after the collision, it's also negative 1 kilogram meters per second if momentum is really conserved. So to answer the question, what is the net momentum of the system before and after the collision, it would be negative 1 kilogram meters per second. And that's it. We're going to study these different types of collisions in class.